welcome. Thanks for joining us. We're going to sit tight for just a few more moments while we wait for a few more people to join, but we'll be getting started soon. Thanks. All right, well, today we are going to be talking about how to reduce cost and lead time with 3D printed soft touch tooling. So Extol's own Andrew Roderick will be presenting, and Andrew is our own additive manufacturing extraordinaire, right, Andrew?
Something like that. Some say applications and sales.
Okay, sounds good. A couple of logistical items to take care of before we get started. So we are going to be recording today's session so that you can review it later in case you have to leave early or you wanted to review something again if you missed it. And we'll be sending that out via email. But let's make sure that everybody can use the chat because we want you to be able to ask questions. And the way that you do that is you go to the top right, and it might actually be open already, but there's a little Q&A icon. It looks like a little chat back and forth with a little question mark in it. And then there should be a button on the bottom to ask a question. And if you click on that, there's a place for your name and there's a place for you to put a question. And of course, you can put a comment there. So how about everybody go over there and do that and then type in where you are participating from today. And whether that's Michigan, Brazil, Canada, Italy, United Kingdom, we've got people registered for this from all over the world. And while you're doing that, I wanted to make note that while this presentation is live, there actually is a short delay, like 10 to 20 seconds. So when we're saying something, you're hearing it 10 to 20 seconds later. The video and all I do will be synced. That's not a problem. But when you are typing things in, it might take us a moment to see it. So when you're asking questions, and we really want you to do that, please ask questions throughout the presentation, and we'll probably address most of those at the end. Just know that there will be a slight delay for when we actually see it. So please ask away. And let's make sure people can use their chat and see if they're, yeah, I can see some of these responses rolling in. We've got people from Michigan and Holland and Weberville and Rockford. Great. Well, Andrew, I'm going to have you take it away.
Thanks, Jason. Good morning, afternoon, or evening to wherever you're at. I'm excited to be with you today and to have a conversation about opportunities that can be realized by each of your companies. So like Jason said, feel free to ask questions. I'm excited to have that conversation as we go through this. So without any further ado, let's get started. Extol is an engineering and innovation company that improves the way plastic products are made. For a little context, Extol supports our customers in 3 areas of our business. First, plastic assembly technology, welding, staking. Secondly, custom automation, so custom machines for assembly. And then thirdly, our engineering services. We have a team of applications engineers to help you with projects. We also have our digital development center where all of our 3D printing takes place. We have 3 5210 MJF printers, and our main goal is to help customers find and develop high-value applications. We can produce parts for you from prototype to production. And I would say the main value proposition why Extol for your additive parts is our unique position with additive manufacturing, as well as our plastic assembly expertise and our innovation process. So this unique approach allowed us to create soft touch tooling and these type of applications. With a systems approach mindset and additive manufacturing, new opportunities in tooling and part fixturing can be realized. Extol's soft touch tooling application is enabled by the technologies of the companies that you see on the screen. So HP, BASF, and Additive Manufacturing Technologies, or AMT. So let's take a high-level look at each of these technologies. HP has brought their multi-jet fusion technology. It's a relatively new technology within the last few years, and it brings new innovation to the additive space with production as the end game. The powder-based system that utilizes agents to assist in the thermal process of IR energy fusing the parts together. The key benefits: consistent print times, part density, and durability, as well as it produces a thermoplastic part that can be joined with traditional welding technologies that Extol provides. BASF's UltraSynth TPU unlocks new applications with its unique characteristics. It's a flexible and durable material, great for shock absorbing situations or applications. Soft touch tooling, non-marking. So in the case of soft touch tooling, design controlled stiffness and durometer can be achieved with design for additive and latticing. And then AMT, Additive Manufacturing Technologies, has their Post-Pro 3D, which is a chemical smoothing process, and it takes soft touch tooling as well as any other application's functionality to the next level. It provides a smooth surface, so you can see the difference between the left-hand unvapor polished part and the finished part on the right. It seals the outer portions of the print, and it allows you to clean the part easier and avoid collecting dust and debris that could hurt your customer's part. So the idea of soft touch tooling came from my background of machine design and being a part of finding better solutions for poured urethane nests. Soft touch tooling can be used as an assembly equipment fixture, shipping dunnage, and the main characteristic is to prevent marking on A-surface parts. A printed soft touch tooling fixture gives the benefit of eliminating CNC and labor associated with poured urethane fixture. It allows you to change the fixture with just changing the TPU upper portion, reprinting that, and giving you better flexibility as your customer part surfaces may change. And it allows for preventative maintenance. If you wanted to put your non-marring portion on a preventative maintenance schedule, that would allow you to do that. So I want to talk through or take you through the journey of how soft touch tooling has evolved here at Extol. We started with traditional manufacturing, right? Poured urethane nest. It's been around for a long time, where you start with a machine base plate, you pour your urethane in a makeshift mold, and then you 3D CNC the urethane. Standard process for assembly fixtures that we've been using on our equipment for a long time. And then we had a customer request an aluminum nest with only a thin portion of urethane. And the process I'm going to show you here, it was our first attempt of satisfying that customer's needs through traditional manufacturing. We started out with a block of aluminum. We were able to CNC the base with an offset, pour the urethane, and then come back through and CNC the final finish of the 3D surface. The next iteration that I'm going to show you now is where 3D printing was first introduced, different technology, but 3D printing nonetheless. So our CNC manager came to me one day with an idea to pour a net-shaped cap with a 3D printed mold. With a few iterations, we were successfully pouring molds. So you start with the raw material, CNC the base, same as the last example, but then we designed and printed a mold, pour the urethane, remove the mold, and then machine the holes at the end. This resulted in less waste material and CNC time, but unfortunately, the designers had to now design and print a mold, which added to overall time. So enter HPMJF and BASF's TPU, and soft touch tooling was born. We were able to print the bases out of the PA12 that you're seeing here. So that's an MJF PA12 part. And then the cap is the TPU from BASF. We're able to print those in parallel on our 35210 printers and assemble the two parts after post-processing. So this approach enables design freedom and speed that are not possible with traditional methods. So after seeing that concept, Jesse, one of our custom machine designers, rose to the challenge and produced the fixture shown here with soft touch tooling to replace the poured urethane supports he had planned to use. So give you a little overview, it's an automotive instrument panel fixture. All of the vertical supports are there to back up InfraStake, which is one of our proprietary staking technologies here at Extol, and then to protect that A surface of the instrument panel. So when Jesse was comparing traditional manufacturing and soft touch tooling, this is what he was able to find. As far as lead time, we were able to blow traditional manufacturing out of the water and take it from days to week, or from weeks to days. For performance, both of them had consistent performance. They performed well. In this specific example, it was a comparable cost. But with added complexity from design freedom, there should be a larger delta between the two, or you might find added value that isn't reflected in that cost, but it's cost prohibitive, so it unlocks that for you. So mileage can vary as far as the specific use case. And then design changes, if your customer was to change the part surface or something like that, the ability to react to those changes drastically is reduced with soft touch tooling additively manufactured. And then design freedom, right? You're able to put as much complexity into the printed part as you can. So you're able to reduce lead time and provide greater design freedom and unlock use cases that weren't available before. So you may say, this doesn't look complex. And at the surface level, you're totally right. Normally when we have backup supports, depending on the geometry, we can use standard bumpers like you see on the left here. But for this specific application and many, the curved surface right underneath the boss for staking is contoured, and we need a really good force backup to ensure a tight welded joint. When you look at this example, each TPU cap here, so there's 23, were unique. So that allows you to have a larger quantity as well as variations, and not have to reprogram or do multiple different things when you're talking the standard CNC route. So one of our early TPU customers put the nest we printed for them to the test to prove out the non-marring capabilities. So this is a chrome-plated pony, and we'll take a look at this video. The initial inspection, so your baseline of what's going on, put it on a cylinder going up and down. It then introduced a 10th offset to get more rubbing and kept the test going. Up to 28,000 times, the tail didn't fare so well with the force introduced with the offset. But when you look at the pony itself, there was no smudges or scratches introduced with the 3D printed TPU. So we did some preliminary performance part marking tests with 4 different part surface finishes. Chrome, PC lens, a matte paint, and a glossy paint. And we tested those 4 with 3 different manufacturing methods: poured urethane, soft touch tooling unpolished, and soft touch tooling vapor polished. The chrome worked well with all situations. The PC lens had some smudging and some scratching when it came to the unpolished, and that's where I was talking about the AMT sealing that surface and not allowing dust and debris to get in there and potentially scratch your part. I'd like to say each specific application should be tested to ensure performance requirements are met. And then with the matte, we had some smudges. We're going to look at that a little bit deeper and what we mean by smudges. And then painted glossy worked real well, had some smudging with the unpolished. So this next video is a video of the matte painted part being tested, and let's take a look at what is referred to as smudging. First, we're going to rub the urethane across the matte paint, and you can see a trail or a mark basically where that was dragged across there. The unfinished TPU a little bit more, and then the vapor polished TPU less. And with each of those smudges, they were able to be rubbed off, not providing or not permanently marking the part. So you may be saying, that's great, but what do I need to consider when designing for soft touch tooling? So let's take a look at that a little bit deeper. The base design could be 3D printed, so it's PA12 in this case, printed on the HP printer. You could choose to use a CNC'd aluminum base plate or contour like this. But in terms of printing, I like to, or it's best to hollow out the base with a honeycomb structure, and this is a service that Extol provides. And for most applications that aren't weight saving, I like to leave this lower surface filled in or have a wall thickness there and just have honey or hollowed out with honeycomb on the inside and leaving unfused powder trapped. This allows for reduced fused material area, which brings down part cost, and leaving the trapped powder on the inside reduces labor so that we don't have to remove the powder out of those deep hexagon recesses. And then as far as attachment to the fixture plate, you can use counterbore holes like shown, large coarse threads would work, or a brass heated insert into the printed part. When it comes to TPU design, the cap, the TPU is more expensive to produce than the PA12. So minimizing the TPU used will put cost only where the value is. So in this case, right next to where your customer part is touching the nest. If you are printing the TPU cap and the PA12 base, a gap interface between the two of 5 to 10 thou has been working well. Being able to design a pokey yoke into the printed PA12 base for ease of assembly is something to take into consideration so that the cap can only be installed one way. And then when it comes to attachment to the PA12 base, you could use a simple flat head screw like is shown in this example, and we're continuing to look at integrated snap features or clip designs moving forward. And as I mentioned, so the AMT vapor fusing process or vapor smoothing process has unique capabilities for the cleanability. And so in this process, it's a chemical. You need to be able to hang the parts into this vapor, and so providing a feature to hang the part from. In this case, we use the hole for the flathead screw. So like I said, we're currently looking at different clip designs, specifically to attach to a machined base plate. This was prompted by a customer looking to combine traditional manufacturing capabilities in-house with the benefits of additively manufactured TPU. So you can see several iterations of the clip design here. Shown here, so you've got a threaded one on the left as well as a snap fit feature on the right. And those are just a couple in a counterbore hole that have shown some promise. So when we look at what makes a great application, in the additive space, complexity is free is a tagline, right? But it's true. Complexity within a component, right? Drive the complexity into the printed part, and you can add value without adding substantial cost. Lead time limitations, if that's a big concern for you, the reduction of lead time is a huge benefit of printed soft touch tooling. And then for small and medium sized nests, high quantity and high part variation is a great fit. So when we take a systems approach, looking at the overall application, taking a step back and being able to look for value-adding features that may not be used or be able to be produced traditionally. Part identification, what could we put into this part to reduce assembly time? So get rid of fasteners, say. Poke yoke to make that smoother. Weight reduction, integrated vacuum cups. I'm anxious to talk with you and explore your application and what we can find value to put into these printed parts. So a customer that we recently went through our proven process of evaluating and developing additive applications had this to say. He said, we learned that a great application for soft touch tooling is providing medium-sized, high-complexity tooling on a large scale. The more we were able to think outside of the traditional manufacturing design box, the more value-adding features we discovered we could incorporate. So that is, I couldn't say it better myself, right? Those are what makes a great soft touch tooling application. So let's look at some questions. Head over to the chat section, submit those questions if you haven't already, and yeah, excited to talk through that.
Thanks, Andrew. As he said, we're going to start taking questions now, so you can go ahead and type some in. There have been a few questions coming in throughout the presentation, so we'll get to those. But real quickly, I wanted to point out that we've got Andrew's contact information on the screen, and we'll send this to you via email later. But we'd like you to email him or call him and try to schedule a time where you can talk about the applications that you have, or maybe you have some detailed questions about the 3D printing in general that maybe isn't appropriate for this venue. But reach out to Andrew. That's a resource for you. It's free. You can set up 15 minutes to just quickly talk through where you might be able to use soft touch tooling. And then coming up, we have another webinar that is scheduled for July 7th, so a couple weeks away. And this is going to be about how to assemble 3D printed multi-jet fusion parts with traditional plastic joining technologies. So if you're interested in learning how these multi-jet fusion parts assemble, how they weld, with whether that's hot plate welding, laser welding, other types of technologies, that'll be a great one for you. And that'll be actually at 1 p.m. Eastern. And there's a link on the screen right now of how to register for that. And I'm also going to paste that link into this meeting chat window. So if it's easier for you to just click on that, you can do that. And you should see that show up in the Q&A section. If you look under featured, the link is there for you to look at. So let's get to some of these questions. The first one that we have is, can you print these two materials at the same time, or can you print two materials in one part?
Yeah, I get that question a lot. Unfortunately, no. With the powder-based system, we're limited to one powder at a time, but we can print them in two different printers in parallel, and then put the two parts together afterwards.
Okay. Another one here, and this one is, how do you assemble the two parts together, or how do you attach the caps to the PA12 supports beneath?
Yeah, so that's application specific. In the use case, we had a threaded hole that we just used a flathead screw to physically attach those two together. But looking at integrated clips, and if you print the base and print the TPU, you're able to open up more opportunities to unique clip and receiver designs. So those are things that we continually are looking at.
All right, and another question here: what level of durability can people expect, and how many cycles of use can the soft touch tooling take?
Yeah, so as far as soft touch tooling in a given application, or you're just putting a part in and out, I would say it's very similar to a poured urethane. We haven't done specific long-term durability, but just the way that it's made and the density and the structure of it, it mimics a molded or a poured durability of the part. Now, if you have a really thin section and there's going to be a lot of flexing and wear and tear in that kind of situation, those are things that we'd want to look at.
All right. And then another one here, what dimensional accuracy are you able to achieve on the base design with PA12?
Yeah, so the PA12, the standard that you can output is plus minus 0.2 millimeters, and then up to 100 millimeters, and after that it's a 0.2% tolerance. And a lot of that is how we orient it. We can make that better, or at least make it so that we're getting the most critical dimensions in the right orientation for you. So that's something that I like to talk through before we print parts, of what are the key features and how can we orient it best for your application.
Great. Another question here. What durometers do you prefer for the caps? Is there a specific one?
So the caps themselves, if you print TPU solid, it's in the 88 to 90 Shore durometer. But I've also printed, say, thin-walled portions with trapped TPU on the inside. That's another way that you can kind of get a spongier feel without designing a specific lattice. But the durometers and the rigidness of the part is very design specific, as far as like you can sky's the limit with latticing.
All right. Do you see a dimensional change in the soft touch caps after the AMT smoothing? So once you vapor polish, does the dimensions change?
Yeah. If you've got further questions on that, feel free to reach out to me. I've got a white paper that I can share with you. But the overall dimensions of the part after the AMT process are changed minimally. It's basically just taking the hills and valleys of the surface and averaging those out with the smoothing process. And a lot of that is in the recipe of the process itself.
Awesome. Well, we've got another minute or so. So if there's any other questions, feel free to put that in. And otherwise, hopefully everybody enjoyed it. And thank you all for attending. And we'll be on our way. Andrew, there was a question here. There's the use case doesn't show a really big cost difference. Can you talk about that a little bit more?
Yeah, so with certain applications, you want to look at the design freedom that soft touch tooling allows and the ability to apply system thinking to achieve a lower overall whole system cost. And you're able to potentially achieve a function that would previously been cost prohibitive. So in this certain example, the cost was similar, but sometimes you may have a similar cost, but it unlocked another feature that you couldn't have before.
Awesome. Well, thank you everybody for joining, and I hope that you found it valuable, and please go and register for the next one if you're interested in that. And if there's any other questions that we weren't able to get to, or you weren't able to type in time, we'll address those via email, or you can write to Andrew, and we'll try to make sure everybody gets their questions answered. So thanks again for everybody. Thanks.
Thank you.